Alright, so today we're going to be looking at representations of SL2 of F. I know last time we looked at did a theoretical look of representations of the special linear Lie algebra. We're going to kind of look at that same structure again, but this time from a more practical basis, more like experimental basis than a theoretical one. We'll start out with a remark here. Recall that SL2 of F, and as always everything's going to be finite dimensional, SL2 has a standard basis of X is the right shift, Y is the left shift, and H is this reflection along the, I think it's along the x-axis. With, I guess I'll show you that out, with our brackets as H bracket X equals 2X, Y on H is 2Y, and X on Y is H. I'm going to look at weights and maximal vectors. So we're going to let V be an arbitrary L module where L is just our SL2 of F, as we recall, H is semi-simple. So, since H is semi-simple, it acts diagonally on our V. And we're assuming that F is algebraically closed, of course, so we have all of the eigenvalues in F. So V is a direct sum of eigenspaces V lambda, where for V and V, the action of H on V is just equal to lambda V for some lambda in F. With V lambda being 0 when lambda is not an eigenvalue. For the endomorphism of V, which represents H. whenever v lambda is non-zero, lambda is called a weight of h in v, and we call v lambda a weight space. You recall, quick reminder, in this case h is just we only have the one diagonal element, so we only have, from last time, we only have the one positive root, so we can talk about all this in the sense of like how that one h specifically is going to act on elements. And comes with a lemma, which should be pretty comfortable here. If v is in v lambda, so the action of h on v scales it, then the action of x on v is in v lambda plus 2, and action of y on v is in v lambda minus 2. And the proof is just by direct computation. We'll go through one case, and the other one is just symmetric. H on this x of v, x of v is just equal to the bracket of h and x on v plus x on h of v, which the bracket of h on x is 2x acting on v, plus h on v gives us lambda, so we can bring that out to the front and get lambda x plus v. And then we can just factor these out into lambda plus 2 x dot v. And the computation works much the same in the case of y. And this implies that x and y are nilpotent endomorphisms of v, but we already know that that's going to be true. Now, since our v is assumed to be finite dimensional, and v as the sum of v lambda, the collection of v lambda, not the sum, is direct. That wasn't even the symbol for sum. There must exist a weight lambda so that the eigenspace of lambda is non-zero with v lambda plus 2 equals 0, so that x acting on v equals 0 for all v in our v lambda. And then any non-zero vector in such a v lambda is called maximal. Called a maximal vector. of weight lambda, of course. So this all is a bit more direct as like an execution of the ideas we learned last time, but this all seems pretty straightforward so far. Now we're moving on to classification of irreducible modules. Now, assume that V is an irreducible L module. Choose a maximal vector say V naught in our V lambda, and we're going to set V sub -1 equal to 0 and Vi equal to 1 over I factorial times y to the I acting on V0. And we have a lemma directly from this. This is kind of our setup. And we have A that H on each Vi is equal to lambda minus 2I times Vi. B, we have that Y acting on Vi. It's going to give us I plus 1, Vi plus 1. And C, we're going to have that X acting on Vi is equal to lambda minus I plus 1 for Vi minus 1 for obviously non-negative I. Now, A is, we saw inductively, we can get inductively from our previous lemma, and B is just like arithmetic, so we only really need to look at C here. We're going to prove C by induction on I. Once again, I equals 0 is automatic because we set V -1 to just be 0. Then we get that I times X on Vi is equal to X times Y times Vi minus 1 just by applying B, which is equal to the bracket of X and Y on Vi minus 1 plus Y on X of Vi minus 1, which is equal to H. In this case, we can just evaluate this bracket to be H on Vi minus 1 plus Y X Vi minus 1. And then we can evaluate both of these because we have it by the inductive hypothesis. The formulas above apply. So this case here gives us lambda minus 2I minus 1 of Vi minus 1 plus, this case we have lambda minus I plus 2 on Y of Vi minus 2, which we can expand this one and give us lambda minus 2I plus 2 v minus I, vi minus 1, sorry, not v minus I, whatever that would mean, plus I minus 1 times lambda minus I plus 2 on vi minus 1, which gives us equal to I times lambda minus I plus 1 vi minus 1. Alright. So by formula A here, by A, we see that the non-zero vi are linearly independent. And we recall that that V is assumed to be finite dimensional. So we're going to let M, and we can pick M to be the smallest integer such that Vm is non-zero and Vm plus 1 is 0. So that every V beyond M is then going to be 0. The formulas above then, from our previous lemma, whatever that was, show the subspace of V with basis of our choice of maximal vector up through Vm is an L submodule non-zero. But if you recall at the start, we assumed that V is irreducible, so this is all of V. And we can write under this basis matrices for the endomorphisms generated, endomorphisms created by X, Y, and H, with H being a diagonal matrix, X being upper triangular, strictly, of course, and Y being strictly lower triangular. as above. Now if we look at this formula C again, if we plug in I to be m plus 1, okay, I'm going to write this here. Plugging index m plus 1 into C, we get the action of x on v to the m plus 1 is equal to lambda minus m, I believe this should be, to vm with vm plus 1 being 0 and vm being non-zero. So that our lambda in this case must be equal to m. Thus, the weight of a maximal vector is a non-negative integer one less than the dimension of our space. This is our highest weight from last time. Highest weight of V. Also, as we expected from last time, each weight occurs with multiplicity of 1. So each of our eigenspaces is, every eigenspace is either one-dimensional or zero-dimensional in this case, depending on whether or not there's actually vectors in it by A, which, if you recall, is that H acting on VI is lambda minus 2I VI. Since V determines lambda uniquely, the maximal vector V0 is unique. Of course, up to scalar multiples. And so we have our results as, you can write them as a theorem. let V be an irreducible module of L being SL2 of F. Then we have seen, first off, that relative to H, V is the direct sum of our eigenspaces, weight spaces, V mu for mu equals m minus 2, all the way down to negative m, where m is 1 less than the dimension of V, and the dimension of each V mu is just 1. Secondly, we have seen that V has up to our scalar multiples a unique, I'll put an asterisk to indicate that's up to non-zero scalar multiples, maximal vector whose weight is just going to be m, MC. The action of L on V is given by the formulas we had there. It's the 3 we created. For appropriate basis, which is just the basis generated by the maximal vector in the way that we saw before. And we saw that there exists at most one irreducible L module, up to isomorphism of course, of each possible dimension m plus 1 for positive m. This comes with a corollary which has quite a bit of discussion following it, and then I guess we're done for this section, this video. This book, I feel like, goes by faster than the others. So corollary, let V be a finite dimensional L module, where L is, of course, SL2 of F. Then the eigenvalues all eigenvalues of H on V are integers. Each occurring with its negative. In any decomposition of V into a direct sum of irreducible submodules the number of summands is the number of dimensions of V0 plus the number of dimensions of V1. And we have our proof. Of course, if V is 0, we're done. So we're going to use Weil's theorem to write V as a direct sum of irreducible submodules. As described by the theorem, which gives us the first part of the corollary, and for the second we observe that each irreducible L module has a unique occurrence of the weight 1 or the weight 0, but not both. Alright. So now they have a bit of a discussion, which I have to figure out how I'm going to present here in this video format. So that really covers all of our a preliminary example of how to apply this to a specific dimension of a special linear V group. But we have a question, open question here still. I'm wondering which this section hasn't answered. Maybe we did it last time. Does SL2F have an irreducible module of each possible highest weight? M in the naturals with 0. So basically we know that the highest weight of a representation can be an arbitrary non-negative integer, but is there actually a representation which has each of those highest weights? Says we have common low-dimensional modules. The trivial module is going to have dimension 1. The natural module, which I believe is just referring to like the 2x2 matrices which make up SL2, which theoretically SL2 is describing as acting on F, which by definition is going to have dimension 2, and the adjoint representation, which describes it acting on itself, since we have 3 basis elements. This is obviously going to be dimension 3. Now, for some arbitrary m greater than or equal to 0, our formulas are 3 formulas from the previous lemma. Can be used to define an irreducible representation of L on an m plus 1 dimensional, an m plus 1 dimensional vector space over F, with, of course, our basis is going to be the highest vector all the way down to Vm, called Vm. With the actual construction they don't have explicitly, but the way you have it is you just, like, I think you would just define each vector, like v0 to our Vm, and then define the representations as being equal to these formulas that we extracted from before. Now, there's one more discussion. I don't know how much of this I'll get, but I'll go through it here. Now, so it's the symmetry of Vm is clear through the exponential map. We're going to find a representation phi from L to the general linear Lie algebra of our constructed Vm. This is going to be the irreducible representation of highest weight m that we constructed above in the last paragraph. Then we know that phi of x and phi of y are going to be nilpotent endomorphisms. Because they just push you through the basis, and so eventually you're gonna like go past the basis on either end and hit a 0. So we may define an automorphism of Vm as taf equal to e to the phi x times e to the phi of the negative y, and then e to the phi of the x, which is a construction we saw before, I think. And we're going to let m be positive, so the representation is faithful. You're seeing that conjugating phi of h by taf is the same as applying, same effect that is, as applying e to the adjoint of phi of x, e to the adjoint of phi to the minus y, e to the adjoint of phi to the x, to our phi of h. Now, as phi of L is L, isomorphic to L, this can be calculated as taf phi of h taf to the inverse, giving us just negative of phi of h, and from this we see that taf sends its basis vector vi of weight m minus 2I to the basis vector vm minus I of weight. It's going to be the negative, which is going to be 2I minus m. If V is a finite dimensional L module, then this taf interchanges positive and negative weight spaces. Alright, I liked being able to look at a more concrete example of what we saw last time, and this should also serve as a good continuation of our warm-up into root space decomposition, which will be our next video, so look forward to that.